All right, so we're experiencing what it likes to have sort of a fast lecture. It re-emphasizes in my mind how much people can't learn just from lectures. I do hope it's helpful, but you do have to do your very best to pay attention. And you also do need to do the reading. And it's ideal to do the reading ahead of time because that's going to make the lecture more meaningful. If you don't do the reading, you may have no idea what I'm talking about. Some of you may be experiencing that right now, okay? Especially when I'm trying to describe these graphs and distributions. So what have we done so far? We talked about histograms, describing distributions, the 5-number summary and box plot to a certain degree. What we need to do a little bit more before we go on to computing and interpreting means and standard deviations is talk about how to actually compute medians, first and third quartile. I should say first and third quartile. Minimum and maximum are easy. Once you've got the data sorted, minimum is the lowest, maximum is the highest. All right, why don't we go ahead and take these unemployment rates actually. Let's see here. I went over here and I sorted them from low to high. By the way, realize that when I do such a thing, I've lost all information about the corresponding states. Because, for example, this row is no longer Alabama, and in fact, you know, this might be, I don't know, North Dakota, and this might be South Carolina or something. I don't know. So by doing this sorting, you should realize that I've lost the information about the states. Okay? But that's okay for the purposes of calculating the 5-number summary. Once you've got these sorted, and by the way, I was checking before class, and I think it's probably better to use, well, okay, if you highlight them, I think it's probably better to use sort range instead of sort sheet. I think the sort sheet can maybe get you into trouble. So it's better once they're highlighted to short range. Anyway, they are sorted. Let's look at 2009. 4.3% was the lowest unemployment rate. That's the minimum. Scroll down. The highest was 15.2%. That's the maximum. So the two numbers in the 5-number summary are very easy to find. The median is the next one you want to find. There are two middle numbers. The median is their average. How do I know there's two middle numbers? Well, there's 50 states total, right? Anytime your data set is an even number like 50, there are going to be two middle numbers. Anytime your data set is an odd number of numbers, then there's going to be one middle number. When there's one middle number, when you have an odd number of data values, that one middle number is the median. When you have an even number of data values and two middle numbers like here, the median is halfway between the two middle numbers. It's their average. The average of 8.6 and 8.8, maybe zoom in to see that. Can you see it well enough in the video? The average of 8.6 and 8.8 is 8.7. The median of the August 2009 data is 8.7. That's the third number in the 5-number summary. How do you figure out where those two middle numbers are? You use a formula to find the location. The location of the middle, I won't say middle number, in either the even or odd case, is n plus 1 over 2. Emphasis on the word location. It's not the value of the median. It's the location. In the case where n is even, like 50, n plus 1 will be 51. Over 2, that's going to be 25.5. The middle location is 25.5 for this example. Meaning if you count down from either the low or count up from the low or down from the high, I guess I have them in reverse order, low is high and high is low. You want to count 25 spots, including the first one. Be careful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, right there. The 25th and 26th number in this case are the two middle numbers. 25 and 26 are halfway between 25. are evenly spaced to 25.5. 25.5 is their average. 51 over 2 is 25.5. So there are two middle numbers on the 25th and 26th position. That idea, by analogy, works whenever you have an even number of numbers. So again, the median here for 2009 is 8.7. How do you find the first quartile and the third quartile? When you've got two middle numbers, include one of them, the lower one, in the lower half of the data. And the first quartile of the entire data set is the median of this lower half. This lower half has 25 numbers in it. An odd number of numbers. There will be a middle number. 25 plus 1 over 2 is 26 over 2 is 13. The 13th number in this lower half of the entire data set is the first quartile of the entire data set. Where is it? 1, don't forget to count the first one. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, I bold-faced it. 7.1 is the median of the lower half of the numbers, lower, mean, lower in value. It's the first quartile of the entire data set. The third quartile of the entire data set is the median of the upper half, upper meaning higher values. There's 25 of those as well. 25 plus 1 over 2 is still 13. Count 13 from this one or from the other one at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It does work the other way too, by the way. Start down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's the median of the upper half of the values. It's the third quartile of the entire data set. That's our method. You should know that technology, like spreadsheets and like calculators, calculates quartiles as well, first and third, but doesn't necessarily give you the exact same answer as our method. That's because there's some debate about the best method of calculating quartiles. Our method is the simplest one for us, and plenty of people use it. We'll go ahead and use it. What if your entire data set had a unique middle number? Like what if n was 51 to start with, if we included, for example, the District of Columbia, which is sometimes included in the unemployment rate list, Washington, D.C. Then we'd have 51 data values, an odd number. 51 plus 1 would be 52. 52 divided by 2 would be 26. There would be one middle number in the 26th spot. To find the first and third quartiles, throw that number out as our method, and consider the lower and upper halves after throwing the median out. The median of the lower half is the first quartile of the entire thing. The median of the upper half is the third quartile of the entire thing. We will throw the median out before deciding lower and upper halves. I suppose you could keep it in, keep it for both lower and upper half, and that would be another method. But that's not the method we will use. We will throw the median out if there is a middle number in the case where n is odd before calculating the first and third quartiles. Okay? I said that verbally. That's something you may want to watch again on the video. All right. And then again, you graph the 5 numbers somewhere with box plots. The rest of our time, we want to spend on calculating means, talking about how to calculate means and standard deviations by hand, so to speak, though it's certainly with calculator help, and become familiar with their formulas. Formulas certainly aren't the most important thing in this course, though sometimes it feels that way. I do want you to know formulas. Actually, for tests, you will be able to use a note card to write formulas on, but it is still worth knowing. And quizzes where you can't use note cards, I might put formulas on. I might, for example, as a multiple choice, say, what's the formula for the standard deviation? And I'll give you options, and you need to pick which one. Okay? Why is it worth learning about formulas? It can give you a little intuition about what to expect. That's partially why you use them. And it also can give you intuition about why the procedures make sense. Okay? Those, to me, are the two main reasons. give you some intuition about expectations and why procedures make sense. Here's the formula for the mean. X bar, again, is the symbol for the mean if you're calling the variable x. If you're calling the variable y, then you call it y bar. If you're calling the variable z, then you call it z bar. Okay? Though usually in stats we reserve z for something else. These numbers, x1, x2, x3, xn, etc., represent the data values. Not necessarily in order from least to greatest. x1 is not necessarily the smallest value. xn is not necessarily the biggest value. By the way, n is the size of the data set. N could be 50, for example, with the states. Then the last number would be x50. These are called subscripts. They're just labels. The entire symbol, x sub 1, x sub 2, x sub 3, represents the individual numbers. Okay? Those are just subscripts. Divide by n. The point is you add up all the numbers and you divide by how many there are. If it helps you, you can write that formula in words. Add up all the numbers, divide by how many there are. But I want you to be familiar with these things too. Here's another way to write it using what's called summation or sigma notation. This funny looking thing is a Greek letter, a capital sigma, and it means add almost always in math. Maybe not always, but almost always. Here's the official way to write add up all the x sub i's, where I kind of represents an arbitrary subscript. 1, 2, 3, 4, etc. I goes from 1 to n is what you say, and then multiply by 1 over n, which is the same as dividing by n. Right? Dividing by a number is the same as multiplying by 1 over the number. So I can write it this way. This is the official way to write it that emphasizes, first of all, that these numbers that you're adding are different. The subscript emphasizes that that I could be 1 or 2 or 3 or 4, etc. All these numbers could be different. They could be the same as well. There could be repeats. But in general, they could be different. It also emphasizes that I starts at 1 and goes up to n. However, it's kind of a pain to always have to write the I. And to always have to write the I equals 1 in the n. So as a shortcut that's sloppy, we sometimes are satisfied, we often are satisfied with this expression. Just meaning add up the x values and divide by n. Multiply by 1 over n. It's sloppy. The main reason it's sloppy because it makes you think that all the x values are the same. Add up the x's that are all the same number? No, it doesn't mean that. The subscript emphasizes the differences. It also doesn't emphasize where I starts. It's implicit that you start with the first number and then go to the ending number. In fact, people will usually be sloppy in this course to save some time. Okay? Here's a formula for the standard deviation, the sample standard deviation, which is what we focus on. It's more complicated. S is the symbol for the sample standard deviation. This is a square root symbol there. We have a fraction inside the square root. Just like with the mean in the top of the fraction, we're adding some things. Just like the mean in the bottom of the fraction, we're dividing by something. N minus 1, mysteriously enough, instead of n. What are we adding in the top? We're adding a bunch of squares. x1 minus x bar squared, meaning, listen carefully, the first data value, x1 minus the mean you just calculated, and then square that number. x2 minus x bar squared, the second data value minus the mean, square that number. Some of these differences could be negative. Right? If x1 is 5 and x bar is 10, 5 minus 10 is negative 5. But when you square it, the negative signs go away. Negative 5 squared is positive 25. You're going to be adding up a bunch of non-negative numbers in the top there. It's possible that a data value could equal the mean and you get 0. But you're never going to get a negative number. No imaginary numbers in this class. No square roots of negative numbers. Okay? You add those up, you divide by n minus 1, then you take the square root. It's very important that you understand the order of operations here. You first find the mean. You've got to find x bar before you're going to be able to use this formula. Once you've got the value of x bar, you've got to calculate all these differences first. Then square those differences. Then add up those square differences. Then divide by n minus 1. Then take a square root. The square root gets done last. Okay? Down here are the summation forms of this formula. Again, this dividing by n minus 1 instead of n is kind of mysterious. Why are we doing that? Wouldn't it make more sense to divide by n? For reasons I won't get into right now, I'm just telling you, divide by n minus 1. Okay? How in the world are we going to use this formula? Okay, let's get a little actual practice out. You should have your calculator. I will make up a small data set. In fact, well, I won't really make it up. I'll take it from our unemployment rates. Alabama, Alaska, Arizona, Arkansas, there's 4 states that start with the letter A. Anybody know the song, by the way? Alabama, Alaska, Arizona, Arkansas.
Well, they call it
That's a great song.
They call it an Alabama song.
Only
Only in Alabama.
All right, there's 4 states there. Let's find the standard deviation of those 4 unemployment rates for 2008. Those are my x values. It's good to make a table to organize your work. I could label this x sub I, and that's probably a better way to label it, but I'll be sloppy. I'll just label it x, but these x's are not all the same. Well, there's almost a repeat there. 4.9, 6.9, 5.6, 4.8. Those are the x values. Let's go ahead and find their sum on the way to finding the x bar. See if I can do this in my head. Actually, a good way to do it in your head is to round these to the nearest whole number, perhaps, and then adjust. Round that to 5, that to 7. Maybe I'll keep that as 5.6. Round that to 5. 5 plus 5 is 10, plus 7 is 17. Plus 5.6 would be 22.6. Then subtract off 0.1, 0.1, and 0.2. 22.6 minus 0.4, 22.2. Is that right? Yeah. Okay. 22.2 is their sum. Probably should put an x here. And then you divide by how many there are. 22.2 divided by 4 is the mean. 11.1 divided by 2 is the same answer. That would be what, 5.55? The mean unemployment rate for these 4 states in August 2008. All right? What's the formula again that we're using? It's right there. Next thing I need to do is I need to subtract these data values from that mean, or the other way around, subtract the mean from the data values. An x minus x bar column, it would be better to use an I there, but we'll be sloppy, we'll be okay with being sloppy. These x's are different. I might as well sort of square it at the same time here. I'm going to run out of boardroom if I don't. So in the first case, the data value is 4.9. The mean again is 5.55. That difference is going to be negative 0.65. Square negative 0.65, you'll get a positive number a bit closer to 0. You know that, right? When you square a number between negative 1 and 1, it gets closer to 0. Oh, my calculator is not full. This calculator is not great. I get 0.4225, it looks like. My 4 is missing a little bit. Oh, though it's showing up on this screen. So I have to line in my calculator. 0.4225. Okay, I'll let you use your calculators right now and figure out these other ones. Do the difference first, then square. 0.9 minus 5.5 is 1.35, square that. 1.8225. 5.6 minus 0.55 is 0.05, square that. Get 0.0025, and 4.8 minus 5.55 is negative 0.75. You don't even need to type the negative sign in here, but do it. Oh, well, that's a problem. Ah, I lost it. 0.35 squared. 0.05 squared, and the use parentheses is negative 0.75 squared. So the 1.8225, 0.0225, oh, excuse me, 0.0025, and 0.5625. I wish this wasn't so long. Let's add those up. The formula says to add those up. I want to use my calculator again. Fun watching me go back and forth. Plus. The formula says add those up, those squared numbers up. When I do that, I get 2.81. People confirm? 2.81. We're almost done. Divide by n minus 1, divide by 3, then take a square root. The sample standard deviation is the square root of 2.81 divided by 4 minus 1, which is 3. Do the division first, then take the square root, which is the same as raising to the 1/2 power. (2.81) divided by 3 is about 0.937. Take the square root of that, you can raise to the 1/2 power. The answer is about 0.9678. Probably we should round that to about 0.97. That's the standard deviation. Approximately 0.97. It's good to put approximately equal to's when things are approximately equal to's. It happens so often that people don't, that I've given up on taking off points for forgetting it.
We appreciate it.
You really should. Okay? There will be other situations where I will not be lenient in that way. Okay? But I'll be lenient in this situation. You should, however, carry as many digits of accuracy along the way and only round at the very end. If you've got a bunch of digits, it's good practice to keep all those digits before rounding at the very end. How do you interpret the meaning of the standard deviation of the mean? That's what we'll end class with today. Get the screen back up here. Maybe I just need to move the computer a little more or something, I don't know. Interpreting the mean and standard deviation in many, but not all, situations. Use normal distributions, also known as bell-shaped curves, or bell curves, or Gaussian distributions. Anytime you hear those words, it means the same thing. The most common word to use is normal distribution. There's a picture I found. You can find many such pictures online from this website illustrating a normal curve. And some important things about it. First of all, let's go ahead and pretend 0 is the mean. Okay? This normal curve, in your imaginations, is supposed to represent an approximation to a histogram or a stem plot. Okay, we're looking at a stem plot or a histogram, and we're imagining drawing a curve over it. As with the temperatures, many data, not all, are relatively symmetric in their stem plots and in their histograms. So a normal curve can be a good approximation. Let's imagine the mean of that data is 0 or very close to 0, so this curve is centered on 0. Okay, maybe our data has some negative numbers, like temperatures, low temperatures in January, negative numbers. These other numbers, the 1, 2, 3, the -1, -2, -3, are sign standard deviations away. This number right here is supposed to represent 1 standard deviation above the mean. This number is supposed to represent 2 standard deviations above the mean, 2 times whatever the standard deviation is. This is supposed to represent 3 standard deviations above the mean. These, with the negative, is supposed to represent below the mean. That's why there's a negative. 1 standard deviation below the mean, 2 standard deviations below the mean, 3 standard deviations below the mean. This kind of curve, also called the density curve, can model many kinds of data. And it's the most common model to use. When the data look symmetric in their stem plot or histogram, this is the most common kind of thing to use. What do these numbers, 68, 95, 99% mean? Basically, when your data look like this, approximately 68% of the data will be between -1 and 1. In other words, between 1 standard deviation below the mean and 1 standard deviation above the mean. About 95% will be within 2 standard deviations of the mean. That's like that rule of thumb that I erased here. And about 99%, or even a little bit more precisely, 99.7% will be within 3 standard deviations of the mean. This is going to be super important in this class. As far as interpreting the standard deviation, then, look at the following. The mean is where the center is. It's symmetric. 1 standard deviation, look where that touches the curve. Well, this picture is not, I shouldn't have picked this picture. This picture is not the greatest, actually. 1 standard deviation above the mean actually is where what's called the inflection point in this graph, which is not right there. It's more like right about there. If you pretend this is a ski hill and you're going downhill, the inflection point is where the graph is steepest, where you're going downhill the fastest. More like right about there. So 1 should really be right about there. This picture is not good. Okay? That's our basic introduction to the normal distribution. We will use it a lot starting next week. See you then.